All right, so this presentation is somehow complementary to what Daniele just said. I'm Alessandro Ederoclite. I'm a tenure track astronomer on time domain astrophysics at the Centro de Estudios de Física del Cosmos de Aragón. I've been hijacking the Surveys 23 hashtag over the last few days. So if you want to tweet about this thing, I've been tweeting about you all, so don't be ashamed. I will also be Instagramming, right? So anyway, most of the people, pardon? Yes. So you can show everything on these slides. So over the last few days, and actually over the last many years of astronomy, time domain astrophysics has been done mostly with one to a handful of filters. This light curve here is my favorite light curve, is the beautiful cataclysmic variable SS sig observed for over 100 years in visual. Several programs have been presented, several programs have been mentioned one way or another, and obviously we're all hoping that Federica is going to be able to join us later to speak about LSST. This is how another LiDAR looks like if you observe it with ZTF and then you fold it over its period, right? You only have 3 filters. That's as much as you can do with these 3 filters. But the other end of the spectrum, allow me to joke, is to do spectroscopy. The problem with spectroscopy is that it is obviously far more informative, but it's more expensive in terms of telescope time. Oops. So, as Valentin was saying the other day, you don't want to follow up, for example, all the objects that LSST is going to give us. So obviously, there's instruments like X-Shooter or SOX, which are ideal for those. Some of the ESO spectroscopic projects, I'm sure about Foremost, I can't remember about Moons, they're going to have a time domain component. ERT, depending on which science case, may or may not be ideal for time domain astrophysics. This is the figure that Daniele was about to show, and is what was just hinted, the beautiful spectroscopic follow-up with of GW170817. So yeah, you can see the beauty of this, right? Do you really need spectral resolution 20,000 to get all the information there? Anyway, but sure, if you go with spectral resolution 50,000, you can do this oops, I'm not sure if you can see it, but this beautiful analysis of the H alpha line in another LiDAR star. And if you're really good, and if you have a very good idea, you can actually see how the spectrum moves and you get a Nobel Prize. I hope everybody has seen this plot. So in Havalambre, we sort of sit in the middle between just a few broadband filters and spectroscopy. So Javier Senarro on Wednesday already showed this. This is the so long awaited. We've been waiting for this for almost 15 years. SAFECA was created 15 years ago for this. I joined the project 12 years ago, and I joined SAFECA 11 years ago for this. This is just one small bit. We already have available for us 6 square degrees, and I can't remember how many hundreds of thousands of objects we have available. And these are, the points here are the 56 filters, right? Covering the whole spectral energy distribution. Unfortunately, there's a few galaxies. Obviously, what I care for are the stars. So you can see how beautifully the filters mark the whole spectral energy distribution. You can, I'm going to keep speaking about this in a moment. So after Carlos Hernandez Monteagudo presentation on Monday and Javier Senarro on Wednesday, you already know everything about Javalambre. You know that Teruel is in the Spanish Lapland. We are about 100 kilometers north of Valencia. So if you ever stop by Valencia or you stop by Madrid, from Madrid is 3.5 hours drive. I can do it in 26. But yeah, if you stop by Spain, this is a spot you cannot miss. We have our Romeo and Juliet story, but this is true. We have the corpses. You can see them. You cannot touch them. It's a little bit there. So, and somewhere in between Teruel and Valencia, we have this observatory. You can see the big telescope, which is the T250 with which we do J-PASS, and this is the small telescope with which we do J-PLUS. J-PASS, as Javier was saying, is this survey in 56 filters, actually 54 plus 2 plus 1. These are the sky areas that we have already observed. This area here that we call mini J-PASS is actually available for everyone. So if you go to archive.cefca.es, you can use VO protocols, and actually you have a sky navigator which is very, very similar to the Sloan one, and you can access and you can navigate and you can get all the spectral energy distributions you want. And J+, which is the one done with this small telescope, only has 12 filters. These are the 3,500 square degrees that we liberated to the whole community 2 years ago. No, pardon, in December last year. And this is how main sequence stars, from the hottest to the coolest, they look. I just picked a bunch so that you would see how they look. And you can see, obviously, that, I know it's silly, 56 filters are more informative than 12 filters, right? Now, the thing is, you can do a step further. You can increase your discovery space if, together with number of filters and depth, you take into account time. And so this is what we're doing. Sorry, this is my catch point. We do astrophysics in real time. So what we do is we use non-photometric weather. At CEFCA, I am the king of non-photometric weather. So I hardly ever miss an observing proposal because I always go like, you know, if you can open the telescope, that time is mine. So with this project, which is called J-VAR, a lot of imagination. All our projects start with a J. I've been considering changing my name to Alessandro. So the program is called J-VAR, Javalambre Variability Survey. And it's a filler. So, you know, we can have clouds, which actually makes the photometry a little bit more complicated. The scene is average, don't ask. And we selected the most efficient filters of the J+ system, which are basically these 6 ones, plus the 395, because that is the one that contains the calcium H&K line, which is an activity indicator. And then we have differential photometry coming to rescue. And this is a plot made by Stelios Pirsas, who's doing the photometric calibration. He's been working on this for almost 2 years now. And by now we are we are confident that it actually works. This is a non-variable star, and actually looks like a non-variable star. So who we are, the PIs are Hector Vázquez Ramió and myself from CEFCA. And the team is mostly located at CEFCA, is Stelios Pirsas, David Morate, Ramon Iglesias, and Alberto Moreno. And the core team is made by Álvaro Álvarez, Beatriz Blanco-Siffert, and Vinicius Blanco. So somehow it inherits the Spanish-Brazilian relation from J-PASS and J+. The observing strategy, we repeat 11 times this oops, this pattern of that you can see here. We observe the 7 filters, we did it a bit, the 7 filters did it a bit, and then we're done. And we repeat this 11 times, and 11 times are whenever the weather is bad. Unfortunately, the weather is not, sorry, unfortunately, the weather is bad not often enough. So yeah, you cannot observe as much as I'd like. Thankfully, Javier is not here. And under some specific circumstances, we actually observe even more. So we're finalizing DR1. I'm going to speak about this a little bit more in a sec, but these are basically the first 102 fields that we had completed. We have slightly over 1 million sources. This is the sky distribution, and you can see that we are following the footprint of J+. So we're staying away from the plane of the Milky Way. We're also trying to compromise with the distance from the ecliptic. And this is a little bit of demography. So we have lots of pulsating, we actually have a lot of pulsating stars, a lot of active stars. Actually, we have more active stars than we were expecting, which is actually interesting. These are the so many variables that we have in each of the bands. So we don't have light curves in all the bands. In some cases, the object is just too faint to be followed up. And just guide you through some of the science cases. This is an eclipsing binary. Possibly this is even more exciting. This is a pulsating star, and you can not only you can do the light curve based on its period, but you can actually build your own color index, and you can see how the color index varies across the period. And of course, this is something that also the VVV people were commenting on Monday. You can build variety of variability indicators, and so we already have a few new variables detected. And for one eclipsing binary, we have the period. So eventually, we're going to publish it. I work specifically on cataclysmic variables. So this is how a cataclysmic variable looks like in ZTF. 3 filters, lots of observations. This is how a cataclysmic variable looks like. These 2 cataclysmic variables look like in J+, only 12 filters, but on 1 epoch only. And this is how they look like for me in J-VAR. So I can see how the spectral energy distribution varies every time I observe it. We can observe optical transients. Of course, we're not driven by optical transients like Van Rouge is, but we can adapt. This is a work which is led by Beatriz Blanco-Siffert, and we have variety of detections. We also had our own discovery a couple of years ago, and rushing a bit because I'm running out of time. David Morate at SAFECA is doing a phenomenal job on asteroids. He has analyzed very much all the R2, and actually he's analyzing in real time, and as soon as we get some new observations. And we have a few thousand objects, which allows us to make a study of the mineralogy of asteroids across the solar system. It's not something that we can't do before, but our filters allow it to do it in an even better way than others. And so this is something that David was showing me just last week. So you can actually see the distribution of carbonaceous versus silicaceous. I have no idea what this is. Minor asteroids in the solar system. Second to last slide. Data distribution is now our headache. That's the reason why I was such a pain in the neck with everyone asking about data distribution. And I want to thank Alberto, Laura, and Mauro for their patience. The problem here is the virtual observatory doesn't have a standard yet. That's just a recommendation. So this makes it a little bit more complicated because we try, especially Tamara Sivera, who's our BO expert, and Tamara tries to follow well and properly BO standards, to the point that when the official BO validator said that one of our protocols was not 100% compliant, turns out that it was the validator that was wrong. And our data, the data we're distributing is not just like us. We want to distribute images and image differences. We make differences with ourselves, reflectances, and obviously light curves. To summarize, there was a very good point. To summarize, use narrowband filters. That this is message number one. Message number two, don't be afraid of fillers. I mean, we saw, was it Atlas, which was a filler, ended up with an average scene of 0.8 arc seconds? That's ridiculous. That's not a filler. Come on. I liked Teresa's point yesterday of IDS versus big telescopes. J-VAR is this beautiful niche, 7 filters, 11 epochs, quasi-random cadence. You can basically observe and you can get anything that varies is there. Say our science would be, officially SPI, I should say, our pillars are asteroids, transients, and variable stars. In fact, is non-variables, new variables, and I steal the acronym from Dante, the what is that objects. I think we're all thinking about something else, not what is that. And this is from yesterday. This is the status of the survey as of yesterday. Oops, I'm speaking too much. So these are the fields, and the color coding tells how many epochs have been observed, and these are the times between observations. Sorry I spoke too much. Thanks.